Well, good afternoon, or good morning. This is 11:37. I'm 7 minutes late getting started for a linear algebra class, but I'm the only one in the room. So let's go on and get started from there. There are a couple of announcements. One that's pretty important that we need to make sure gets said, but wait till someone comes in before I say it, just so I know someone will hear it. No guarantee that anyone will hear it if I say it just into this, because I don't know who listens to these. So anyway, we're in Chapter 2, Matrices, and Section 2.1, and we were just about to do Example 7, top of page 47. Okay, so let's write it down. Here's a linear system. Let me get my pen set up. Okay. X plus 2, x of 1, plus 2x of 2, plus 3x of 3. Let me clean that up just a little bit. Okay. Is equal to 0. 4x of 1 plus 5x of 2 plus 6x of 3 is equal to 3. And 7x of 1 plus 8x of 2 plus 9x of 3 is equal to 6. Okay. Now, there's your system, linear system of equations. Okay? Says this can be rewritten into, oh, there's somebody coming in. All right. Good to see you here. Gotta find my pen here. I can mark you. Okay. You are now marked. Okay. Before I do anything else, let me put on the projector and with the lights. Okay. I said earlier when I was getting started, there's a couple of announcements. One's really important, but I wanted to wait till someone was here to guarantee someone heard it.
Is it the same one from yesterday?
The one about the FAFSA?
Yes.
You heard it yesterday?
Yes, sir.
Yes, I did.
Yes.
Okay. I couldn't remember if you came in before or after I announced that. So you've heard that, and you know about the college transfer day tomorrow and Thursday. Tomorrow in Birmingham, this one, and then the research experience for undergraduate.
Yes.
So you've heard them all. Okay. So got you here. That's good. So here's our system of equation, a linear system. Okay? Now, for some reason, they're wanting to rewrite this as a matrix. And what they say here doesn't exactly jive with what I understand a matrix system. Here's what they say: AX is equal to B. Now, indeed, what that would be the matrix. You tell me what matrix that would be.
Is it 1, 2, 3, 0?
No, not yet. We're not doing. We're writing it in this form.
4, 5, 6, 7, 8.
Okay, times your x vector is x of 1, x of 2, x of 3, and your equality, not doing the Gauss-Jordan like you were starting to do, is this 0, 3, 6. Now, thinking back, this is a multiplication here, and it's a 3 by 3 times a 3 by 1. You can do those, and that gives you 3 by 1, and sure enough, that's what we get. And if we look at this, it'll be x1 plus 2x2 plus 3x3 is equal to 0. That's the first one for it. Yeah, it just goes right down the line. That gives you that. Now, that's not how they wrote it in the book. That's what they said could be written as, but then they broke it this way, okay? And this is what they had done earlier, but this isn't the same as what they said. You can do this as 147 times x sub 1 plus 258 times x sub 2 plus 369 times x sub 3. And that's equal to 0, 3, 6. Now let's see if indeed that's true too. X sub 1 plus 2x sub 2 plus 3x sub 3 is equal to 0, 4. Yeah, that's exactly that, you know. So this is written that way. This is written partitioning these out, okay? Just another way of writing it, okay? Now, and then this is the part that sort of drives me a little nuts. Now they do using Gauss elimination. Well, if we're going to use Gauss elimination, why didn't we start with the way you were going to say it in the first place, okay? And when you do, excuse me, okay, neither of these forms is particularly great to use Gauss elimination. You have to go back and actually do Gauss elimination, which would be 1, 2, 3, just like you were going to say before, 0, 4, 5, 6, 3, and 7, 8, 9, 6. Okay? Perfect attendance today. Way to go. Okay? Well, we've gained one and lost one. Okay? Yeah, I know. I'm just kidding. You heard the announcement about FAFSA for next year?
Yeah.
Okay, good. And then you heard about the college day and all that kind of stuff that's coming up. I figured you were here for that one, but I wanted to make sure of that. Pretty important. So, what would be your first step in Gauss elimination on this one? Now, notice they say Gauss elimination, not Gauss-Jordan. So, yeah, what would you say? I'm sorry?
Is that a 4?
Yeah.
Negative 0.
-4, row 1 plus row 2 is the new row 2. And make that a 0. Okay? That's probably not what you said, but that's what I heard. Okay? Using row 1, so it's 1, 2, 3, 0. And what's your new row 2?
0.
0.
Negative 3.
-3.
Negative 6.
-6. 3. Okay. What's next? Yeah. Times row 1 plus row 3 is a new row 3. Okay? So what would that yield us? 0. negative 14, negative 6. Okay, next. Negative 12 and 6. Okay. Now, before you do anything else, like the next temptation probably would be to divide everything in row 2 by negative 3, right? You want a 1 there, right? And you could do that, and it's perfectly legitimate, but what I would suggest is right now do negative 2, row 2, plus row 3, and make that the new row 3. I put my thing on that side, I had more room. And what would you get then? Leaving the top alone, 1, 2, 3, 0. Now, after I do what I'm going to do there, I'm going to do what I just said, dividing everything by negative 3, which would make it 0, 1, 2, negative 1. Okay, but using the row 2 before I did that, what would you get then? 0. Negative negative 3 would be, huh?
Oh, negative 2 times negative 3?
Yeah.
Yes, 18.
It's what?
18. Negative 2 times negative 3. I mean, whoa, 6. I'm sure.
Yeah, okay, got it.
Sure.
What would that give us? 6. We're doing this thing here to that, okay? Okay. Plus row 3. 0. 0. 0. Okay. Which is sort of good. Because if we would have wound up with a 0, 0, 0, 15 or 4/3 or something, no solution at all. It would never work. But with all zeros, yeah, that'll be fine. So we do have, we're in Gauss elimination, not Gauss-Jordan, but Gauss elimination. So what would we do at this point? Okay, no. We're not doing Gauss-Jordan. If we were doing Gauss-Jordan, yeah, that would be what we would do. Gauss elimination we're through.
Substitution.
Except what?
We do substitution now.
I think that's what you're meaning is called parameterization. Pick a parameter. Which one would you use as a parameter? Second?
Z is equal to T.
T. And what will be the T? The one without a leading 1, which would be x3. Okay? Okay? Then, what would be your x2? Okay, plus 2t is equal to negative 1. So that would be x2 equal, whichever way you want to do it, minus 2t minus 1. Okay? And your x1. Okay, well, it's a 2 and then a minus 2t minus 1. Just plug in what the x2 is. Plus 3 times t is equal to 0. Right? So that would mean that x1 is equal to 3t plus 4t would be 7t minus 1. Whoa, looks pretty hairy to me. So your ordered triplet for your x1, x2, x3 would be 7t minus 1, comma, minus 2t minus 1, comma, t. Okay. Now, if I did it right, it's not looking too good. So if you let, I think I've got an error here somewhere. Because if you let t equal 0, then you would have a minus 1, 0. Right? And let's see if that would work. Minus 1, no, that doesn't work. So I made an error somewhere here. I think we're okay up to the end down here, but here we have t equal x3, x2 is equal to minus 1 minus 2t, and x3, or x1 would be,
That's
I think there's a minus, huh?
that'd be negative 4t.
Yeah, that's it. Minus 4t, plus, it's on the same side, I'm sorry. So that'd be a minus t, wouldn't it? Okay. Minus t minus 1, isn't it? No, when you move it to the other side, and it becomes plus 2, right? Okay, I don't know where my head is today, but let's see if we can get it right. Okay, you get x1 minus 4t plus 3t, that would be a minus t equals 0, so move that to the other side, and you have a minus 2, move that to the other side, it becomes plus 2. So it would be t plus 2. Okay, now let's try again. If t is equal to 0, you'd have 2 minus 1, 0, and sure enough the first one would be 2 minus 2 plus 0 is 0. Okay, I won't do the rest of them, I think they're right. Now, they said 1, 1, negative 1. Let's see. So if t is negative 1, this would be a 1. That would be a 1. Yeah, 1, 1, negative 1 would work. Okay. Infinitely many solutions, one of which is 1, 1, negative 1. Why they chose that one, I'm not sure. That is, B can be expressed as a linear combination of the columns of A. And that's, so they're saying put that in here. 1, 5, 7. And then put in any value you want. They chose 1 plus 2, 5, 8. Also times 1 plus actually 3, 6, 9 times negative 1 equal 0, 3, 6. Okay, just sort of an observation. Let's see if that's right. 1 plus 2 is 3, minus 3 is 0. 5 plus 5 is 10, minus, that's a 4. I don't know how that became a 5. Boy, not doing well today. Okay. 4 plus 5 is 9, minus 6 is 3, 7 and 8 is 15, minus 9 is 6. Yeah. So that certainly works. And any linear combination that you take by putting any t in there will work as well. Okay? So that's what this is showing. B can be expressed as a linear combination of the columns of A. This representation of one column vector in terms of others is a fundamental theme of the linear algebra. So that's why we were doing it. It's a fundamental theme of linear algebra. Now, it says, just as you partition A into columns and X into rows, it is often useful to consider an M by N matrix partitioned into smaller matrices. And then they give an example here: 1, 2, 0, 0, 3, 4, 0, 0, negative 1, negative 2, 2, 1. And it looks like what their goal was is to block out or partition out those 4 zeros by themselves and then let the rest land where they wanted to. They don't say what you do with them, they just say you can partition that way. Or partition a matrix into column matrices. And that same matrix, have the first column be 1, 3, negative 1, second column 2, 4, negative 2, third column 0, 0, 2, and the last column 0, 0, 1. Or row matrices, in the first row 1, 2, 0, 0 is R1, 3, 4, 0, 0, R2, and negative 1, negative 2, 2, 1, R3. They say you can do that. They don't say what you do with it, but you can do it for sure. And then the linear algebra applied, and this is pretty incredible. Many real-life applications of linear systems involve enormous numbers of equations and variables. For example, a flight crew scheduling problem for American Airlines required the manipulation of a matrix with 837 rows, no, that's not on the airplane, and more than 12,750,000 columns, 750,000 columns, to solve that application of this application of linear programming. Researchers partitioned the problem into smaller pieces, solved it on a computer. So that would be some problem to do. Glad we're not doing one of those. Okay. Exercises 2.1, do any of the either 1 or 3. They're both at Calc Chat. Any of the odds 5 through 9, they should all be at Calc Chat. Any of the odds either 11 or 13, they should both be at Calc Chat. Any of the odds 15 through 27, they should all be at Calc Chat. 29 to 35 should be at Calc Chat. 37 should be at Calc Chat. 39 to 47 should be at Calc Chat. 49 or 51 should be at Calc Chat. 53 should be at Calc Chat. 55 at Calc Chat. Now, here again, they come up with introducing a new concept in the exercises. Why don't they put it in the section and then ask about it? 57, and that's should be at Calc Chat, and 59 should be at Calc Chat. Ooh, there's more. 61 is a guided proof, and it should be at Calc Chat. 63 or 65 should be at Calc Chat. And again, they're coming up with a new concept here, the trace of a matrix. And that would be the trace of an n by n matrix. A is the sum of the main diagonal entries. That is, the trace of A would be A11 plus A22 plus A33 up to A sub n. Only works for square matrices, and they don't have to be symmetric matrices or anything else. just any square matrix, the trace is the sum of the diagonal components. So 63 and 65 should be pretty easy to do. 67 is a proof. You can do either 69 or 71. They should all be at Calc Chat. 73 is an exploration. You can look at that for Calc Chat. 75 is another proof. It should be at Calc Chat. 77 should be at Calc Chat, as should 79. So choose any of the odds 79 through or 81. They should both be at Calc Chat. Block multiplication, 83 should be at Calc Chat. 85 is a true false. It should be at Calc Chat. And 87 should be at Calc Chat. So let's move on to properties of matrix operations. We've seen how to .1 was operations. Now we're going to look at properties. Okay. 2.1, operations with matrices. And now 2.2 will look at the properties of these matrix operations we were just talking about. So catching the sort of the link of all this. Okay. 2.1, you concentrate on the mechanics of the three basic matrix operations. Matrix addition, which includes subtraction, scalar multiplication, and then matrix multiplication. This section begins to develop the algebra of matrices, how you put all those together. You'll see that this algebra shares many, but not all of the properties of algebra of real numbers. And here is a statement of those. Now, all of you have your books with you, so let me do these. Theorem 2.1, A, B, and C are M by N matrices. Okay? C and D are scalars. Then these properties are true. First, A plus B, two same size matrices, is the same as B plus A. Yeah, I mean, if you do element by element, each element is a real number, and A plus B is the same as B plus A for every element in there. So yeah, that one holds. Pretty obvious. Okay, and that you could call the commutative property of matrix addition. Okay, of course the two matrices have to be the same size for that to happen. Okay, number 2. If you're adding matrix A to the sum of B and C, of course they're all three the same size, so you can do this. That's going to be the same as adding matrix A to matrix B and then adding that to matrix C. That's the associative property of matrix addition. Okay? Now, here's sort of a associative property of multiplication. Okay? And that's if you have two scalars, C, D, times matrix A, that's the same as C times the product of DA. Okay? Now they're calling this the associative property of, I'm going to put scalar multiplication. They just say multiplication. I don't buy that because it's not all multiplication, not multiplying matrices. Okay? Number 4. This is similar to one we have in real numbers. The I don't know what they really mean here. Both are true. They've written 1 times A is equal to A. Obviously that's true. Okay? But it's also true that I times A is equal to A. They didn't write a I, they wrote a 1. That's why I had to do a double take here to make sure I was reading that right. But both of these are true. 1 times A is equal to A, but it's also I times A is equal to A. Now, these are two different facts here, so let me separate those. This is true only if I is the right size. And what the right size would have to be would be an M by M matrix, because the identity matrices are always square, and in order to multiply these, I don't think this is what they meant now. Now that I look at it, I bet you this, because they'd have to have already said this. I would have to be M by N, M by M, because M by M times an M by N, you can do that, and that gives you an M by N. And so that would be true only for the right size I sub M, I sub M, okay. So I don't think that's what they meant, but this is the, they say multiplicative identity, which is okay. With 1 that's just so patently obvious, but I think that's probably what they really meant. Okay, that's supposed to be a 5, that's an ugly 5. Now, here is one distributive property, C times B plus A is equal to CB plus CA. Okay? Why did I write them backwards? I don't know. Okay, that's correct, but the book put A first and B second, and I don't know why I wrote it backwards. Okay, it works backwards too. Okay, now I would call this distributing a scalar across the sum of two matrices. I'll just do it. They're writing very short titles for theirs, because number 6 is also a distributive property, but it's C plus D times A, and that would be CA plus DA, oops, capital A, and that's distributing a matrix across the sum of two scalars. Okay, they're both distributive properties, but obviously not the same distributive property. All right, they do a little proof on at least one of them, maybe two, which I think I've already talked through part of that. So let's do example 1. Should be pretty simple. Anyone need this any longer? Okay. To obtain the sum of 4 matrices, add the corresponding entries as shown below. Now, of course, the 4 matrices have to be the same size, and both of these, all 4 of these are 2 by 1s. 1, 2, plus a negative 1, 1, negative 1, negative 1, if I could read, plus a 0, 1, plus a 2, negative 3. They claim this is equal, well, let's us figure out what it's equal to. Okay. Top entries, 1 minus 1, that's 0, plus 0 is 0, left with just a 2, right? The second one, here we have a minus 1 and a plus 1, that adds a 0, 2 and a negative 3, that would be a negative 1. what I did some associative and commutative and variety of things like that. But you got 2 and -1, and that's exactly what they got there. One important property of the addition of real numbers is that the number 0 is the additive identity. That is, C plus 0 is always C. Never fails, right? Okay. For matrices, there is a similar property, but you have to specify size. So if A is an M by N matrix, and O that's supposed to be, I think, a 0 M N matrix, okay? Then it is the additive identity for all M by N matrices. So this is a 0 matrix, it's M by N, so whatever M by N you had, when you add it to this 0 matrix, that will always be 0. So, and they give, for example, a 2, 3, 0, 2, 3 would be 2 rows, 0, 0, 3 columns, 0, 0, 0, 0. Not a very exciting matrix, but certainly true. That would be the 0 matrix for any 2 by 3 matrix. Now, when the size of the matrix is understood, you can denote the 0 matrix by either 0 or they bold it. I can't bold, so I'm going to put an arrow over it. I don't particularly care for that because to me, that's the 0 vector. It could be a column vector or a row vector, but I would not look at that and think matrix. But they're using that symbology here, so that's fine. Now, the properties of 0 matrices are listed next in Theorem 2.2, relatively easy to prove, and the proofs are left as an exercise, for example, 65. So let me, I think I'll erase this so I have more room to write. Goodness, I grabbed me a granola bar between classes. It didn't do much good. I'm so starving. Okay. So here we have Theorem 2.2. We start with A being an M by N matrix. Okay? C is a scalar. Then the following properties are true. 1. A plus the 0 M by N matrix is going to be A. Okay? 2, A plus, and well, they don't give names for these, plus the negative of A is equal to the 0. Okay? M by N. Now, I'll leave that alone. I'm going to say one more thing about that, but it's not really necessary. Now, here's the one that sort of matters big time. If CA is equal to the 0 M by N matrix, then this implies that either C is equal to 0 or A is itself the 0 M by N matrix. Okay? One or the other. That's as close to a 0 product principle as you're going to get with matrices. And notice it's the product of a scalar times a matrix. And if that does give you the zero m by n matrix, then either C's got to be a zero and A could be any m by n, or A is also the zero matrix of whatever it's C, you multiply that, you won't get it. That's what you get. This does not work for two matrices, the matrix multiplication. No guarantee of that. Okay. Only scalar multiplication. Now, a couple more observations. Real numbers. X plus A is equal to B. What you can do is subtract A from both sides, and you get X is equal to B minus A. Okay. They duplicate it, but a little bit differently. Same thing holds here. If you have matrix X plus matrix A equal matrix B, then it's perfectly legal to subtract matrix A from both sides, and that leaves you X is equal to B minus A. Goodness, I'm having trouble writing my letters properly. Okay, B minus A. Okay. Sorry, I think I got an eyelash in my eye or something. Stinging like crazy. Okay. Now, they carry this to gory extremes, but, you know, it still works. All right. Let's do example 2. Okay. We've still got probably 30 minutes or so, right?
25.
25, okay. I was just going by the time that has elapsed here. All right. Solve for X in this equation. 3X, matrix X, plus matrix A is equal to matrix B. Okay? Where A is equal to -1, -2. No, that's 1, -2. 0, 3. Okay. The B is -3, 4. Two, 1. Okay. Given that A and B, it says solve for X. So I would just as soon do everything I could before I start plugging in numbers. So let's first subtract A from both sides. Okay. And that gives you, this goes to 0. 3X is equal to B minus A. Okay, sorry about that. I don't pay attention. My pen drags like crazy. Okay, and then divide both sides by 3. Okay, so X would then be, first do B minus A. It's not so awfully bad, is it?
So it's B minus A.
Yeah. -4 is the first entry. Okay. 6. Yeah, I can't get this thing out of the way. If I wait and let the pen touch the paper, it does all sorts of weird things, or screen, not paper. And now, it won't erase. I don't know what's going on. Okay. Negative 2, no, 2, right? And negative 2. Okay. And we're going to divide that by 3, so this would be minus 4/3, 2, 2/3, negative 2/3. All right, that's your matrix X. Make sure we got the same thing, negative 4/3, 2, 2/3, negative 2/3. I guess we lost. Maybe he's coming back. I don't know. All right. Let's look at properties of matrix multiplication. Basically, most of what we were doing there was matrix addition. Some scalar multiplication, and some with zero matrices. But let's look at properties of matrix multiplication. And again, excuse me, you'll notice some similarities between multiplication properties of real numbers and multiplication of matrices, but you'll see a few glaring errors, or not errors, things that aren't in matrix multiplication. So where we're starting here is A, B, and C are matrices. Now, with sizes such that the matrix properties are defined, what I'm going to put appropriately sized. Okay. And what I mean by that is the multiplications can happen. When we write them down, they can happen. What that means, these will be shifting sizes through these various things. Okay. C is a scalar, and C is a scalar. All right. So these properties would be true. First of these, if you do A times the product of BC, that's going to be the same as AB times C. Now, let's start out by generically giving sizes for these things. What size you want A to be? Pick any two letters. M by N, those are the ones I was going to pick. Okay? Now, that is going to, and because this has to be an M by N, that's going to limit something about B. What are you going to know has to be true about B? N by something, okay? And let's do N by P. Okay. Well, then we just determined this has to be an N by P. So that says C has to be something. What does it have to be? P by something. Let's just call that something Q. So this will be a P by Q. Okay? Now let's see if everything works out okay. Size-wise. And again, appropriately sized so that multiplications can work. Okay. Do what's in parentheses first. This has to be an N by Q product here, right? And you can multiply that by M by N, And that would give you a product that's M by Q, right? Okay, so the left-hand side has to be an M by Q. I can't write, but it's somewhere there. This product that you do first, because it's in parentheses, that's an M by P. And when you multiply that by P by Q, then the P's go out and you get an M by Q. So sure enough, that's the sizes work. This is telling you everything works, okay? If the sizes didn't work, then this couldn't be true. So this is the associative property of matrix multiplication. Okay, and of course the sizes have to be correct for it to happen. Okay, number 2. If you have A times the product, the sum of B plus C. Now obviously these are different sizes in 2 than they were in 1. They have to be. Why? What do you know about those? Right off the top, what can you tell me about sizes of some of those? I would suggest do the parentheses first. What would have to be true? Yeah, B and C would have to be the same size. They couldn't be up here unless they were square. So everything's changing between these two. So this means, do you want to name a size for B and C? I don't care. M by N? Is that what you said? Once you do it there, you have to do it everywhere. Okay, or you might have said M and M's because you were hungry, but that we can't. We're not going to limit ourselves to square. Okay, what would A have to be then? Okay, want to do a PM? Okay. And if this is a PM, does everything match there? Well, this sum would have to be an M by N, and then these two can be multiplied and you get a P by N. And these M's would go P by N, and these M's go and you get a P N, and when you add 2 P N's you get a P by N. Yep, that works too. At least size-wise it does. This is a distributive property of matrix multiplication over matrix addition. And they just say distributive property, which is fine, you know. Now the C one. 3 one. Where did I get C? Okay. This time we have A plus B times matrix C, and they're claiming that has to be A, C plus B, C. And again, it doesn't take too much effort to see. These have to be the same, so let's call them M by N, M by N, N, and the sum has to be an M by N. So C would have to be an N by P or something like that, and then you get an M by P. Okay, and then using those same sizes we just had, A we said was an M by N, C was a N by P, B was an M by N, and C was an N by P. These two can certainly be multiplied and come up with an M by P. These two multiply, come up with an M by P, and your sum of 2 M by P's would have to be and M by P. Yeah, everything works there size-wise. And this tells you this is another example of distributive property of matrix multiplication over matrix addition, but it's done in the reverse order. So this is actually just exactly the same. All right. The fourth one is sort of a cheapie. And since I've run out of room here, you do it. And that's C times AB is equal to CA times B, which is also equal to C times AB. No, I said that won't work. When I was writing, I said that can't be true. That would be A times CB. That can work, okay? Of course, this would indicate if A is an M by N, B must be N by something. Let's just call it M by P. So this would be a M by P, and multiply a scalar by it, still M by P. So this is an M by N, and multiply a scalar by it, still an M by N, multiply that by M by P, and of course you get an M by P. And this would be an M by N. Can't write. And this would be still an N by P, and this would be an M by P. Whew. Okay. They didn't even name that one. It's best I would call it was the associative property of a scalar with two vectors multiplication of two vectors is sort of an associative property. Okay. Now, let's do example 3. Okay. Find the matrix product ABC by grouping the factors first as AB times C and then A times BC. So, exercise in multiplications. Here's A is 1, negative 2, 2, negative 1. B 1, 0, 2, 3, negative 2, 1. Okay, and C. Negative 1, 0, 3, 1, and 2, 4. Okay. So they first want us to do AB, multiply that by C. Okay? My knee stiffens up on me if I sit too long. Okay, so let's do AB. Can you do AB? A is a 2 by 2, B is a 2 by 3. Sure enough, that product will be a 2 by 3, because you wipe out these two and you're left with a 2 by 3. So what would be the 1, 1 entry here? All right. Yes, and 1 negative 6 would be negative 5. Good. The 1, 2 entry would be positive 4. The 1, 3 entry would be zero. Okay. The 2, 1 entry would be negative 1. The 2, 2 entry would be positive 2. Is that what you said? Yeah. Got it. And then the 2, 3 entry would be 3. All right. Let's take that and multiply it by C. Well, can we do this? That's a 2 by 3 times a 3 by 2. And what answer will you get? A 2 by 2. I shouldn't write down numbers there. I should write down blanks. Okay, beep, 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 beep. Okay, so let's do the 1, 1 entry. $17. The 1, 2 entry. Oh, okay, I was looking at it wrong. Okay, 0, yep, 4. Okay, the 2, 1 entry. $13. And the 2, 2 entry. Oh, I think 5. I think 14. Okay, maybe I'm doing wrong. We're doing 2, 2.
Is that a 4 or a 9?
I think that's a 4. Okay, sorry about that. Let me see if I can find it again. Yeah, it's a 4. Sorry, probably my lousy writing. Okay, and I got 17, 4, 13, 14. Yeah, that's what Lady got. That's doing one way. How are we doing on time? 4 minutes. I think we can do the next. What we want to do next is A times BC. So let's do BC first. Well, B is a 2 by 3, and C is a 3 by 2. So this is going to give us a 2 by 2. All right, let's do those two. Ooh, hurt. Three. Wait, what did I just do? Getting in a hurry and doing weird things. Okay. All right. 1, 2. Okay. 0, 0, 8. Yeah. Okay. 2, 1. That's what I got. And last. 2, okay? And now let's multiply that by A. Well, A is a 2 by 2, BC is a 2 by 2, so this is going to be a 2 by 2 as well. All right, let's see if we can do that quickly. 3 minus 14 is minus 11. That's not good. Okay, something's wrong here.
No, that's 16 now.
Okay, sorry. A times BC. 3
That's negative 13.
minus, plus 14. 3 plus 14 is 17, right? You're doing 1, 1. So it's be 3 plus 14 is 17. A times BC. Which one? The A?
I put the BC in front.
Oh, okay. Yeah, not commutative, okay. You just showed it, okay. The 1, 2 entry would then be 8 minus 4 would be 4, right? 2, 1 entry and then the 2, 2 entry, 16 minus 2, 14. Yep, got the same thing. And it wasn't just because they picked just the right matrices to do it. It indeed is a property. Okay, I'm guessing we must be close to being out of time, are we?
Yeah.
Okay. So we'll begin next time with example 4, top of page 55. But before we do, put this in place, homework exercises here. I think you can do any of the odds 1 through 5. They're all at Calc Chat. I think you can do any of the odds 7 through 11. They should be at Calc Chat. I think you can do 13. It should be at Calc Chat. I think you can do 15 through 21. They should be at Calc Chat. '23 should be at Calc Chat. And then we'll stop there and pick up the rest of them later. All right, good deal. Okay. See you tomorrow.
Yep.